What's up, everybody? This quick video explains the difference between row major and column major storage orders and its impact on performance. We will write a small C++ program that shows the impact of memory latency by iterating over a matrix in column major order and row major order. In the interest of saving you time, here is the difference between proper and improper access of a matrix. In each of these cases, a 10K by 10K matrix represented as an array, a two-dimensional STL vector, and a dense matrix from the eigen library is iterated over both row-wise and column-wise. The performance impact is dramatic. Let's begin. Let's first take a look at this picture. Modern systems have multiple layers of memory between the processing unit and main memory, with the modules with the quickest times also being the smallest. Here we have the CPU and main memory. It is very quick for the CPU to fetch data from L1 and L2 caches, which are closest to it, roughly 1 nanosecond for the L1 cache and 5 nanoseconds for the L2 cache. We will simply refer to these collectively as cache. A fetch operation from main memory is much slower, roughly 60 to 100 nanoseconds. I've linked Peter Norvig's blog post in the description below, which describes these timings in more detail. Memory is addressed linearly. We can imagine it as a strip. Address 1 equals address 0 plus an offset, address 2 equals address 1 plus an offset, so on and so forth. When we ask the CPU to read an item from main memory, it will prefetch some additional items and store them in cache in case it needs them. Note that our two-dimensional matrix is written as a one-dimensional strip that we will be indexing into. That two-dimensional decomposition into a one-dimensional representation is done in either column major format or row major format. Spatial locality refers to the principle that if an item is referenced, nearby items will tend to be referenced soon. This is the basis for much of computer architecture. The CPU transfers data in cache lines and prefetches cache lines in an attempt to predict what we will likely need next. It thinks that if we accessed a certain address in main memory, that there is a high likelihood of us requesting access to nearby addresses as well. Keeping this in mind, what does proper access look like? Well, proper access minimizes the number of times the CPU has to go out to main memory. Elements that are prefetched are not discarded without being used. What does improper access look like? Elements that are prefetched are discarded repeatedly. Repeated cache misses end up imposing a very large performance penalty. It is also important to note that this is not something the compiler can optimize away, regardless of the compiler flags. So let's see if any of that holds up in practice. I have some helper functions here to time the code, and what we are going to do is we will just do nested loops, compare the timings on them for arrays, vectors, and dynamic matrix from eigen. And that's a very straightforward, very simple code that we're going to write. So let's do that. Notice that the inner loop is incrementing over elements of each of the columns that have been theoretically prefetched in each iteration of the outer loop. Let's run that, see what we get. So yes, so it's a row major data structure, and row-wise iteration over it is much, much faster than column-wise, where we're basically repeatedly going out to memory, main memory, and hunting around for that index, that value, and discarding the prefetched items repeatedly. Let's do the same thing for 2D vectors and see what we get there. And let's do that for dynamic matrix from the eigen library as well. Let's run that and see what we get. Okay, so that's interesting. Just because your language is a row major language or has a certain storage order, you cannot just assume that whatever BLAST library it is that you're using has the same storage order. In fact, most BLAST libraries have column major storage orders. So this could be low-hanging fruit for optimization in your code base. And that about does it. If you enjoyed this video, hit the like button and consider subscribing. See ya.